What if the key to exploring the farthest reaches of the universe lies not in building faster ships, but in bending the very fabric of reality itself? Imagine a future where the stars are no longer out of reach, where the vast distances of space are no longer a barrier, but a gateway. This is the promise of space-time curvature, a concept that could redefine how we think about travel, time, and the universe itself. Today, we're diving into 25 groundbreaking theories on how space-time curvature could revolutionize the way we explore the cosmos. From wormholes that act as cosmic shortcuts to black holes that could slingshot us across galaxies, these ideas push the boundaries of science and imagination. Each theory offers a glimpse into a future where the impossible becomes possible, where humanity's reach extends beyond the stars. So, buckle up and get ready to explore the cutting edge of futuristic travel. By the end of this journey, you'll not only understand the science behind these incredible ideas, but also see how they could shape the future of life as we know it. Let's begin. Now, let's step into the fascinating world of wormholes, cosmic shortcuts that could change the way we think about space travel. Imagine a tunnel that connects two distant points in space-time, allowing you to travel from one end to the other in an instant. This is the essence of a wormhole, a concept rooted in Einstein's theory of general relativity. According to his equations, space-time can bend and warp, creating pathways that could, in theory, link faraway regions of the universe. These tunnels, often visualized as a folded piece of paper with a hole punched through it, offer a tantalizing possibility, bypassing the vast distances of space entirely. But here's the catch: wormholes, as they exist in theory, are incredibly unstable. They would require immense amounts of energy to keep them open, and even then, they might collapse almost instantly. This is where exotic matter comes into play. Exotic matter, with its negative energy density, could theoretically counteract the natural tendency of wormholes to collapse, providing the stability needed for travel. However, exotic matter is purely hypothetical at this point, and we have yet to discover or create it. Another challenge is the sheer scale of energy required. The energy needed to create and sustain a wormhole is beyond anything humanity has ever harnessed. Some scientists speculate that advanced civilizations might one day tap into the power of quantum fields or even dark energy to achieve this. Others suggest that microscopic wormholes formed naturally in the quantum foam of space-time could be scaled up with the right technology. Despite these hurdles, the idea of wormholes as cosmic shortcuts remains one of the most exciting possibilities in the realm of space-time travel. They represent a bridge between the known and the unknown, a potential key to unlocking the mysteries of the universe. And while we're still far from making this a reality, the journey to understand and harness wormholes is already pushing the boundaries of science and imagination. As we move forward, let's explore how these theoretical tunnels could become traversable and what it would take to turn this dream into a reality. Now, let's take a closer look at what it would take to make wormholes not just a theoretical concept, but a practical reality. The key to creating traversable wormholes lies in exotic matter, a hypothetical substance with properties that defy our everyday understanding of physics. Unlike ordinary matter, which has positive energy density, exotic matter possesses negative energy density. This strange property could counteract the natural tendency of wormholes to collapse, effectively propping them open and making them stable enough for travel. But here's the challenge: exotic matter has never been observed in nature, and creating it in a lab remains beyond our current capabilities. Scientists speculate that it might exist in the form of quantum fields or as a byproduct of advanced technologies we have yet to develop. Some theories even suggest that dark energy, the mysterious force driving the accelerated expansion of the universe, could be harnessed to produce the negative energy needed for wormhole stabilization. While these ideas are still in the realm of speculation, they offer a glimpse into the kind of breakthroughs that might one day make traversable wormholes possible. Recent advancements in quantum physics have also sparked new hope. Researchers are exploring the behavior of particles at the smallest scales, where the fabric of space-time itself becomes fuzzy and unpredictable. In this quantum foam, tiny wormholes might naturally form and disappear in an instant. The idea of scaling up these microscopic tunnels, using advanced technologies to stabilize and enlarge them, is a tantalizing possibility. Imagine a future where we could manipulate the quantum fabric of space-time, turning fleeting phenomena into permanent pathways for travel. Another exciting development comes from the field of materials science. Scientists are investigating the properties of metamaterials, engineered substances with unique electromagnetic properties that could mimic the effects of exotic matter. While these materials are still in their infancy, they represent a step toward the kind of technological innovation needed to make wormholes a reality. Combined with advancements in energy generation and gravitational manipulation, these tools could one day bring us closer to unlocking the secrets of traversable wormholes. Of course, the journey from theory to practice is filled with challenges. The energy requirements alone are staggering, and the risks of destabilizing a wormhole mid-journey are immense. But as we continue to push the boundaries of science and technology, the dream of traversable wormholes remains a beacon of possibility, a reminder that the universe is full of wonders waiting to be discovered. With this deeper understanding of what it might take to make wormholes traversable, let's turn our attention to another groundbreaking concept, the Alcubierre Drive, a theoretical engine that could warp space-time itself to achieve faster than light travel. Now, shifting our focus to another revolutionary idea, let's explore the Alcubierre Drive, a concept that could redefine our understanding of space travel. Unlike traditional propulsion systems that push a spacecraft through space, the Alcubierre Drive proposes a radical alternative, bending space-time itself. Imagine space as a stretchy fabric. Instead of moving across it, the drive would contract space in front of the spacecraft and expand it behind, effectively creating a warp bubble. Inside this bubble, the spacecraft remains stationary relative to the local space-time, while the bubble itself moves faster than light. This means the ship wouldn't break the cosmic speed limit set by the speed of light. Instead, it would ride a wave of distorted space-time. The idea, first proposed by physicist Miguel Alcubierre in 1994, is rooted in Einstein's theory of general relativity. According to the equations, space-time can be warped, and if enough energy is applied in the right way, it's theoretically possible to create this warp bubble. But here's the catch: the energy requirements are astronomical. Early estimates suggested that the drive would need the equivalent of the mass energy of an entire planet or even a star to function. This has led many to dismiss the concept as purely speculative. However, recent research has offered a glimmer of hope. Scientists have proposed that by refining the shape of the warp bubble or using exotic matter with negative energy density similar to what we discussed with wormholes, the energy demands could be significantly reduced. Some calculations now suggest that the energy required might be within the realm of possibility, though still far beyond our current capabilities. Another challenge lies in the mechanics of the drive itself. Creating a stable warp bubble requires precise control over space-time curvature, something we're only beginning to understand. Even if we could generate the necessary energy, we'd still need advanced technologies to manipulate space-time on such a scale. This has led researchers to explore alternative approaches, such as using quantum fields or harnessing dark energy, to achieve the same effect. While these ideas are still in their infancy, they represent a step toward making the Alcubierre Drive more than just a thought experiment. Despite the hurdles, the potential of the Alcubierre Drive is undeniable. If realized, it could allow us to travel to distant stars and galaxies in a fraction of the time it would take with conventional methods. Imagine reaching Alpha Centauri, our nearest stellar neighbor, in just a few years instead of millennia. The implications for exploration, colonization, and even contact with extraterrestrial civilizations are staggering. While the Alcubierre Drive remains a theoretical concept for now, it serves as a powerful reminder of how far our understanding of physics could take us and how much we have yet to discover. With the Alcubierre Drive offering a tantalizing glimpse into the future of space travel, let's now turn our attention to another fascinating idea: overcoming the immense energy barrier required to make such a device a reality. Now, let's dive deeper into one of the most daunting challenges of the Alcubierre Drive: overcoming the colossal energy barrier. As we've already touched on, the energy required to create a warp bubble is staggering. Early estimates suggested it would take the equivalent of the mass energy of an entire planet or even a star. This has understandably made the concept seem like science fiction to many. But here's where things get interesting. Scientists are exploring innovative ways to reduce these energy demands, bringing the idea closer to reality. One promising avenue is the use of exotic matter with negative energy density. This type of matter, which we've discussed in the context of wormholes, could theoretically help stabilize the warp bubble while drastically cutting down the energy needed. While exotic matter remains hypothetical, its potential applications in space-time manipulation are too significant to ignore. Researchers are also investigating whether quantum fields or other advanced physics concepts could provide alternative pathways to achieving the same effect without requiring such extreme energy inputs. Another intriguing possibility lies in harnessing dark energy, the mysterious force driving the accelerated expansion of the universe. If we could tap into this vast, unseen energy source, it might provide the power needed to warp space-time. While our understanding of dark energy is still in its infancy, some scientists believe that future breakthroughs in cosmology could unlock its potential for propulsion technologies. Imagine a future where we're not just observing dark energy, but actively using it to propel spacecraft across the cosmos. Advanced fusion reactors also offer a potential solution. Fusion, the process that powers stars, could provide a nearly limitless source of energy if we can master it. While current fusion technology is still in development, progress is being made, and some experts believe that fusion reactors could one day generate the immense energy required for space-time manipulation. Pairing fusion with advanced energy storage and distribution systems could make the Alcubierre Drive more feasible than ever before. Of course, these solutions are still speculative, and significant technological hurdles remain. But the very fact that we're exploring these ideas shows how far we've come in our understanding of physics and engineering. The Alcubierre Drive may seem like a distant dream today, but with continued research and innovation, it could one day become a cornerstone of interstellar travel. As we continue to push the boundaries of what's possible, let's shift our focus to another fascinating concept: black hole slingshots and how they could revolutionize space travel. Now, let's turn our attention to a concept that sounds like it's straight out of a science fiction novel but is grounded in real physics: black hole slingshots. Imagine using the immense gravitational pull of a black hole to slingshot a spacecraft across the cosmos. It's not just a wild idea, it's a theoretical possibility that could revolutionize how we think about space travel. Black holes, with their incredibly strong gravitational fields, could act as natural accelerators. By carefully navigating a spacecraft close to a black hole's event horizon, the point of no return, we could harness its gravity to gain tremendous speed. This technique, known as a gravitational slingshot, is already used in space missions today, such as when spacecraft use planets like Jupiter to gain momentum. But with black holes, the effect could be exponentially more powerful, potentially propelling us to speeds that would make interstellar travel feasible. However, this approach comes with significant risks. One of the most well-known dangers is spaghettification, a process where the intense gravitational forces near a black hole stretch objects into long, thin shapes like spaghetti. For a spacecraft and its crew, this would be catastrophic, but here's where advanced technology comes into play. Scientists are exploring the possibility of developing ultra-strong shielding materials that could withstand these extreme forces. These shields would need to be incredibly resilient, possibly incorporating exotic materials or advanced energy fields to protect the spacecraft from being torn apart. Another challenge is navigating the chaotic environment around a black hole. The intense gravitational forces can distort space-time, making it difficult to predict trajectories accurately. Advanced navigation systems powered by artificial intelligence and real-time data processing could help spacecraft adjust their paths dynamically, ensuring they stay on course and avoid being pulled into the black hole itself. While the idea of using black holes as slingshots is still in the realm of theory, it's a fascinating example of how we might one day leverage the most extreme objects in the universe to explore the stars. The risks are real, but so is the potential. With continued advancements in technology and our understanding of black holes, this daring concept could become a cornerstone of future space travel. As we venture further into the possibilities of space-time manipulation, let's explore another intriguing idea: navigating the event horizons of black holes and how they might offer even more opportunities for travel. Now, let's take a closer look at what lies beyond the edge of a black hole's gravitational grip, the event horizon. This boundary, often called the point of no return, is where the pull of gravity becomes so strong that not even light can escape. But what if we could find a way to navigate this extreme environment? Could the event horizon itself become a tool for travel? One intriguing idea is the concept of safe zones near the event horizon. These are regions where the gravitational forces might be balanced in such a way that a spacecraft could orbit the black hole without being pulled in. Think of it like surfing a wave. You're riding the edge of immense power, but with precise control, you could stay just outside the danger zone. Scientists speculate that advanced propulsion systems and real-time navigation tools could allow a spacecraft to hover in these safe zones, using the black hole's gravity to accelerate without falling in. But there's another fascinating aspect to consider: time dilation. As predicted by Einstein's theory of relativity, time slows down near a black hole due to its intense gravitational field. For a spacecraft orbiting close to the event horizon, time would pass much more slowly compared to someone observing from a distance. This means that while years might pass for people on Earth, only days or weeks could pass for the crew aboard the spacecraft. This effect could be both a challenge and an opportunity. On one hand, it could complicate communication and coordination with mission control. On the other hand, it could allow for incredibly long journeys to distant stars within a single human lifetime, at least from the perspective of the travelers. Of course, navigating the event horizon isn't without its risks. The gravitational forces are so extreme that even small miscalculations could be disastrous. Advanced artificial intelligence systems would be essential for making split-second adjustments to the spacecraft's trajectory, ensuring it stays within the safe zone. Additionally, the intense radiation and particle streams near the event horizon would require robust shielding and energy management systems to protect both the spacecraft and its crew. While the idea of using black hole event horizons for travel is still speculative, it opens up a world of possibilities. By mastering the delicate balance of gravity and time, we could unlock new ways to explore the universe. As we continue to push the boundaries of our understanding, the event horizon might not just be a barrier, it could become a gateway. Next, we'll shift our focus to another groundbreaking concept: the creation of localized space-time bubbles and how they could revolutionize the way we travel through the cosmos. Now let's turn our attention to a concept that feels like it's straight out of science fiction but is grounded in real theoretical physics: space-time bubbles. Imagine wrapping a spacecraft in a protective bubble that shields it from the chaotic forces of the universe. This isn't just about physical protection, it's about manipulating the very fabric of space-time itself to create a smooth, isolated environment for travel. The idea of space-time bubbles revolves around creating a localized distortion in space-time around a spacecraft. Think of it like a force field, but instead of deflecting physical objects, it alters the space-time around the craft. By doing this, the bubble could effectively isolate the spacecraft from external gravitational forces, turbulence, and even the effects of acceleration. This would allow for a much smoother journey, free from the jarring forces that would otherwise make high-speed travel uncomfortable or even dangerous. One of the key benefits of space-time bubbles is their potential to reduce the strain on both the spacecraft and its passengers. Without the need to constantly counteract external forces, the craft could maintain stability and efficiency even at incredible speeds. This could be especially useful for long-distance travel, where the cumulative effects of gravitational forces and cosmic turbulence could otherwise wear down both the vessel and its crew. But how would we create such a bubble? Theoretically, it would require advanced manipulation of gravitational fields, possibly using technologies we've only begun to imagine. Some scientists speculate that exotic matter or energy sources could be used to generate the necessary distortions in space-time. Others suggest that breakthroughs in quantum physics might one day allow us to pinch off a section of space-time, creating a self-contained bubble that moves independently of the surrounding universe. Of course, the challenges are immense. Maintaining the stability of a space-time bubble would require precise control over the forces involved. Any imbalance could cause the bubble to collapse, potentially trapping the spacecraft or exposing it to the very forces it was designed to avoid. Additionally, the energy requirements for creating and sustaining such a bubble would likely be astronomical, pushing the limits of our current understanding of physics and engineering. Despite these hurdles, the concept of space-time bubbles offers a tantalizing glimpse into the future of space travel. By isolating a spacecraft from the chaotic forces of the universe, we could unlock new possibilities for exploration, making journeys across the cosmos not only faster but also safer and more comfortable. As we continue to explore the boundaries of space-time manipulation, the idea of space-time bubbles reminds us that the universe is full of untapped potential. Next, we'll dive deeper into the challenges of maintaining and controlling these bubbles, and how breakthroughs in quantum physics and materials science could bring this futuristic concept closer to reality. Now, let's take a closer look at what it would take to keep these space-time bubbles stable and under control. While the idea of creating a protective bubble around a spacecraft sounds incredible, the reality is that maintaining such a structure is no small feat. Stability is the key challenge here. Imagine trying to hold a soap bubble steady in a gusty wind, now scale that up to the size of a spacecraft and the forces of the cosmos. That's the kind of precision we're talking about. One of the biggest hurdles is ensuring the bubble remains intact over long periods. Space-time bubbles would need to withstand not only the natural gravitational forces of nearby stars and planets, but also the unpredictable effects of cosmic radiation and interstellar dust. Any instability could cause the bubble to collapse, leaving the spacecraft vulnerable to the very dangers it was designed to avoid. To address this, scientists are exploring the role of exotic matter, a hypothetical substance with negative energy density that could help stabilize the bubble's structure. This exotic matter would counteract the natural tendency of space-time to snap back into its original shape, effectively keeping the bubble intact. Control is another critical factor. Even if we could create a stable bubble, we'd need a way to maneuver it through space. This would require precise manipulation of the bubble's boundaries, almost like steering a ship through a storm. Advanced quantum computing could play a role here, providing the computational power needed to calculate and adjust the bubble's shape in real time. By integrating quantum sensors and actuators, we might one day develop systems that can detect and respond to external forces instantaneously, ensuring the bubble remains stable and on course. Materials science also holds promise for overcoming these challenges. New materials with unique properties, such as ultra-lightweight yet incredibly strong alloys, could be used to construct the framework of the bubble. These materials would need to interact seamlessly with the gravitational fields generated by the bubble, allowing for precise control without adding unnecessary weight or complexity. Breakthroughs in nanotechnology could further enhance this, enabling the creation of materials that can self-repair or adapt to changing conditions, ensuring the bubble remains stable even in the harshest environments. Of course, the energy requirements for maintaining and controlling a space-time bubble are staggering. Current estimates suggest that the energy needed would far exceed anything we're capable of producing today. However, advancements in energy generation and storage, such as harnessing dark energy or developing ultra-efficient fusion reactors, could one day make this feasible. The key will be finding a way to generate and sustain the necessary energy without overwhelming the spacecraft systems. While the challenges are immense, the potential rewards are equally groundbreaking. A stable and controllable space-time bubble could revolutionize space travel, making it faster, safer, and more efficient than ever before. As we continue to push the boundaries of quantum physics and materials science, the dream of traveling through the cosmos in a protective bubble of space-time may not be as far off as it seems. Next, we'll explore how quantum entanglement could open up entirely new possibilities for instant travel across the universe. Now, shifting our focus to the fascinating realm of quantum mechanics, let's dive into the idea of using quantum entanglement for instant travel. Quantum entanglement is one of the most mind-bending phenomena in physics, where two particles become so deeply connected that the state of one instantly influences the state of the other, no matter how far apart they are. This connection seems to defy the speed of light, raising the tantalizing possibility of using it to transmit information, or even matter across vast distances in the blink of an eye. At its core, quantum entanglement relies on the principle that particles can exist in a shared state, meaning their properties are intertwined. For example, if one particle is measured to have a certain spin, its entangled partner will instantly exhibit the opposite spin, regardless of the distance between them. This instantaneous link has led scientists to speculate about its potential for communication or travel. Imagine being able to send a message, or even a physical object, from one end of the galaxy to another without the delays imposed by the speed of light. It's a concept that could revolutionize not just space travel, but also our understanding of the universe itself. However, the road to making this a reality is fraught with challenges. One major limitation is the difficulty of controlling and maintaining entangled states over long distances. While entanglement itself is instantaneous, the process of creating and preserving these connections is incredibly delicate. Any interaction with the environment, such as exposure to heat or radiation, can disrupt the entangled state, a phenomenon known as quantum decoherence. This makes it extremely challenging to use entanglement for practical applications like travel or communication. Another hurdle is the issue of measurement. In quantum mechanics, the act of measuring a particle's state collapses its wave function, effectively destroying the entanglement. This means that while entangled particles can influence each other instantly, we can't directly use this connection to send meaningful information without breaking the link. Scientists are exploring ways to overcome this, such as quantum teleportation, where the state of one particle is transferred to another without physically moving the particle itself. While this has been successfully demonstrated on a small scale, scaling it up to the level needed for interstellar travel remains a distant dream. Energy requirements also pose a significant barrier. Creating and maintaining entangled states on a large scale would demand immense amounts of energy, far beyond what we're currently capable of producing. Additionally, the technology needed to manipulate and control entangled particles with the precision required for travel is still in its infancy. Breakthroughs in quantum computing and materials science could one day make this feasible, but for now, the idea remains largely theoretical. Despite these challenges, the potential of quantum entanglement for instant travel is too compelling to ignore. If we could harness this phenomenon, it would open up entirely new possibilities for exploring the cosmos, allowing us to traverse distances that would otherwise take millennia in a matter of moments. As research in quantum physics continues to advance, the dream of using entanglement for travel may inch closer to reality. Next, we'll explore how overcoming quantum decoherence could bring us one step closer to making this futuristic vision a reality. Now, let's take a closer look at one of the biggest obstacles standing in the way of using quantum entanglement for travel: quantum decoherence. This phenomenon occurs when the delicate entangled state of particles is disrupted by interactions with their environment, such as heat, radiation, or even stray electromagnetic fields. Think of it like trying to have a quiet conversation in a noisy room. The more interference there is, the harder it becomes to hear what's being said. In the quantum world, this noise can completely destroy the entangled connection, making it nearly impossible to maintain coherence over long distances. To overcome this, scientists are exploring ways to shield entangled particles from external disturbances. One promising approach involves using ultra-cold environments, like those found in quantum labs, to minimize thermal noise. By cooling particles to temperatures close to absolute zero, researchers can reduce the chances of decoherence, allowing entangled states to last longer. Another strategy is to create quantum error correction codes, which act like a kind of spell check for quantum systems. These codes can detect and correct errors caused by decoherence, helping to preserve the entangled state even in less than ideal conditions. Advancements in quantum computing are also playing a crucial role in tackling this challenge. Quantum computers rely on maintaining coherence in their qubits, the quantum equivalent of classical bits, to perform calculations. As researchers develop more robust qubits and better error correction techniques, they're gaining valuable insights into how to stabilize entangled states over longer periods. For example, topological qubits, which are inherently more resistant to decoherence, could one day provide a more reliable foundation for quantum communication and travel. Another exciting development is the use of quantum repeaters. These devices act like relay stations, extending the range of entangled connections by breaking the distance into smaller, more manageable segments. By entangling particles over shorter distances and then linking these segments together, quantum repeaters could help maintain coherence across vast interstellar distances. While still in the experimental stage, this technology holds immense promise for overcoming the limitations imposed by decoherence. Of course, these solutions are still in their early stages, and significant hurdles remain. Scaling up these technologies to the level needed for practical space travel will require breakthroughs in materials science, energy efficiency, and computational power. But as our understanding of quantum mechanics deepens and our technological capabilities grow, the dream of using entanglement for instant travel becomes a little more tangible. With these advancements, we're not just inching closer to overcoming quantum decoherence, we're also opening the door to a future where the vast distances of space could be traversed in the blink of an eye. Next, we'll explore how time dilation, another fascinating consequence of relativity, could be harnessed as a tool for travel, offering a completely different approach to exploring the cosmos. Now, shifting our focus to another mind-bending concept, let's explore how time dilation, a fascinating prediction of Einstein's theory of relativity, could serve as a powerful tool for travel. Time dilation occurs when time passes at different rates for observers in different gravitational fields or moving at different speeds. In simpler terms, the faster you move or the stronger the gravity you experience, the slower time flows for you compared to someone in a weaker gravitational field or at rest. This means that, in theory, you could travel into the future by experiencing time at a slower rate than those around you. Imagine this: you board a spacecraft capable of traveling at a significant fraction of the speed of light. As you accelerate, time for you begins to slow down relative to people on Earth. After what feels like a few years to you, you return to Earth only to find that decades or even centuries have passed for everyone else. In essence, you've effectively traveled into the future. This isn't science fiction, it's a direct consequence of the laws of physics as we understand them today. The implications of time dilation for interstellar exploration are profound. For instance, astronauts on long-distance missions could experience significantly less time passing than those on Earth, effectively reducing the perceived duration of their journey. This could make it possible to reach distant star systems within a human lifetime, even if the trip would take thousands of years from the perspective of Earth. However, this also raises intriguing questions about the social and psychological effects of returning to a world that has aged far more than you have. Time dilation also has implications for human lifespans. If we could harness this phenomenon, it might allow us to extend our effective lifetimes by slowing down our personal experience of time. While this wouldn't stop aging in the biological sense, it could enable individuals to witness events far in the future that would otherwise be beyond their reach. This could revolutionize how we think about long-term projects such as interstellar colonization or the preservation of knowledge across generations. Of course, there are significant challenges to overcome. Achieving the speeds or gravitational conditions necessary for noticeable time dilation would require immense energy and advanced propulsion technologies. Additionally, the effects of prolonged exposure to high speeds or intense gravity on the human body are still poorly understood. But as our understanding of physics and engineering continues to advance, the idea of using time dilation as a travel tool becomes less of a distant dream and more of a tantalizing possibility. As we ponder the potential of time dilation, it's worth considering how this phenomenon could reshape our understanding of time itself. Could we one day use it to explore the far reaches of the universe or even to glimpse the distant future? The answers may lie in the next breakthroughs in physics and technology. Up next, we'll dive into the practical applications of time dilation, exploring how it could be harnessed to make interstellar travel more feasible and what that might mean for humanity's journey among the stars. Now, let's take a closer look at how time dilation could be practically applied to revolutionize space travel. One of the most exciting possibilities lies in reducing the perceived travel time for astronauts embarking on long interstellar journeys. Imagine a scenario where a spacecraft is capable of traveling at speeds close to the speed of light. For the astronauts on board, time would pass more slowly compared to those on Earth. This means that while decades or even centuries might pass on Earth, the astronauts might only experience a few years of travel. This could make it feasible to reach distant star systems within a single human lifetime, even if the journey would take thousands of years from Earth's perspective. To put this into perspective, consider a mission to Proxima Centauri, the closest star system to our own, located approximately 4.2 light-years away. At current propulsion speeds, such a journey would take tens of thousands of years. But with a spacecraft traveling at a significant fraction of the speed of light, the astronauts might only experience a few years of travel time due to time dilation. This would not only make interstellar exploration more practical, but also open up the possibility of establishing human presence in other star systems. Another practical application of time dilation could be in the realm of deep space communication. As spacecraft venture further into the cosmos, the time delay in communication with Earth becomes a significant challenge. However, if we could harness time dilation, we might be able to synchronize communication in a way that reduces the perceived delay for both the astronauts and mission control. This could enable more efficient coordination and decision-making during critical moments of a mission. Of course, there are significant challenges to overcome. Achieving the speeds necessary for noticeable time dilation would require breakthroughs in propulsion technology, such as advanced fusion drives or even antimatter engines. Additionally, the effects of prolonged exposure to high speeds on the human body, including potential impacts on health and cognition, would need to be thoroughly studied. But as our understanding of physics and engineering continues to evolve, the dream of using time dilation to make interstellar travel more feasible becomes increasingly within reach. As we consider these possibilities, it's worth reflecting on how time dilation could reshape our approach to space exploration. Could we one day use this phenomenon to send missions to the farthest reaches of the galaxy or even beyond? The answers may lie in the next generation of scientific discoveries and technological innovations. Up next, we'll explore another fascinating concept, the idea of folding space-time to bring distant points closer together, and how this could further transform our ability to traverse the cosmos. Now, shifting our focus to another groundbreaking idea, let's explore the concept of folding space-time. Imagine if we could bend the fabric of the universe itself, bringing two distant points closer together, almost like folding a piece of paper to connect its edges. This idea, rooted in the principles of general relativity, suggests that space-time isn't just a static backdrop but a dynamic, malleable structure that could be manipulated under the right conditions. At its core, space-time folding relies on the idea that massive objects like stars or black holes can curve space-time around them. If we could somehow replicate or amplify this effect artificially, we might be able to create a shortcut between 2 points in space. Think of it as creating a bridge that bypasses the vast distances of the cosmos, allowing us to travel from one point to another without traversing the entire expanse in between. One of the most intriguing methods proposed for achieving this is through the use of cosmic strings, hypothetical one-dimensional defects in space-time that could act as natural pathways for folding. These strings, if they exist, would have immense gravitational fields capable of warping space-time in ways that could bring distant regions into close proximity. Another speculative approach involves the manipulation of exotic matter or negative energy, which could theoretically stabilize a folded region of space-time, making it traversable. While these ideas remain firmly in the realm of theory, they open up fascinating possibilities. For instance, if we could fold space-time, a journey to a star system thousands of light years away might become as simple as stepping through a doorway. The implications for interstellar travel, colonization, and even communication are staggering. However, the challenges are equally immense. The energy requirements for such a feat are beyond our current capabilities, and the technology needed to manipulate space-time in this way is purely speculative at this stage. As we ponder the potential of space-time folding, it's worth considering how this concept could redefine our understanding of distance and travel. Could we one day unlock the secrets of bending the universe to our will, or will these ideas remain confined to the pages of science fiction? The answers may lie in the next wave of scientific breakthroughs. Up next, we'll dive deeper into the engineering challenges of folding space-time and explore the technologies that might one day make this dream a reality. Now, let's take a closer look at what it would actually take to engineer space-time folds. The idea of bending the universe to our will sounds like something straight out of science fiction, but if we break it down, the challenges and possibilities become clearer. To begin with, the energy required to manipulate space-time on such a scale is almost unimaginable. Current estimates suggest that folding space-time would demand energy levels comparable to those produced by entire stars or even more. This raises the question, where would we get that kind of power? One speculative solution lies in harnessing the energy of black holes or tapping into the mysterious properties of dark energy, which is thought to make up a significant portion of the universe. While these ideas are still far from practical, they highlight the kind of breakthroughs we'd need to make this a reality. Another major hurdle is the technology itself. To fold space-time, we'd need tools capable of generating and controlling immense gravitational forces. One possibility involves the use of cosmic strings, hypothetical, ultra-dense filaments left over from the early universe. These strings, if they exist, could act as natural anchors for space-time, allowing us to create stable folds. However, detecting and manipulating cosmic strings would require advancements in both gravitational wave detection and materials science. Imagine building a machine that could not only locate these strings, but also interact with them in a way that bends space-time without tearing it apart. It's a daunting task, but not necessarily an impossible one. Beyond cosmic strings, another speculative approach involves the use of exotic matter or negative energy. These materials, which defy the usual rules of physics, could theoretically stabilize a folded region of space-time, preventing it from collapsing or becoming unstable. The challenge here is that exotic matter has never been observed in nature, and creating it in a lab would require a deep understanding of quantum mechanics and particle physics. Some scientists have even proposed using advanced gravitational manipulation techniques, such as creating artificial black holes or manipulating space-time on a quantum level. While these ideas are still in their infancy, they offer a glimpse into the kind of innovations that might one day make space-time folding possible. Of course, even if we could overcome these technological and energy challenges, there's still the question of control. How would we ensure that a folded region of space-time remains stable and safe for travel? One idea is to use advanced computational systems to monitor and adjust the fold in real time, much like how modern aircraft rely on autopilot systems to maintain stability. This would require not only powerful computers but also a deep understanding of the physics involved. It's a complex puzzle, but one that could unlock entirely new possibilities for exploration and travel. As we consider these challenges, it's worth remembering that every great leap in human history began as a seemingly impossible idea. The engineering of space-time folds may sound like a distant dream today, but with continued research and innovation, it could one day become a reality. Up next, we'll explore another fascinating concept, gravitational wave surfing, and how ripples in space-time could propel us to the stars. Now, let's shift our focus to a concept that feels almost poetic in its elegance, gravitational wave surfing. Imagine riding the ripples of space-time itself, using the natural undulations of the universe to propel a spacecraft forward. Gravitational waves, first predicted by Albert Einstein over a century ago, are ripples in the fabric of space-time caused by massive cosmic events like the collision of black holes or neutron stars. These waves carry immense energy, and if we could harness them, they might offer a revolutionary way to travel through space. The idea of gravitational wave surfing hinges on detecting and interacting with these waves. Unlike traditional propulsion methods that rely on fuel or external forces, this approach would use the energy of space-time itself. Picture a spacecraft equipped with advanced sensors and a propulsion system designed to catch these waves, much like a surfer catching an ocean wave. By synchronizing with the wave's frequency and direction, the craft could theoretically ride the wave, gaining momentum without the need for conventional fuel. However, the challenges here are significant. First, gravitational waves are incredibly faint by the time they reach us. Detecting them requires ultra-sensitive instruments, like the Laser Interferometer Gravitational Wave Observatory, or LIGO, which has successfully observed these ripples. But detecting a wave is one thing, harnessing its energy for propulsion is another. the energy density of gravitational waves is extremely low, meaning we'd need to find a way to amplify or concentrate it to make it useful for travel. This could involve developing new materials or technologies capable of interacting with space-time in ways we've never attempted before. Another hurdle is timing. Gravitational waves are fleeting, lasting only fractions of a second. To surf them effectively, a spacecraft would need to predict their arrival and position itself perfectly to catch the wave. This would require real-time data processing and navigation systems far beyond what we currently have. Imagine a spacecraft that not only detects gravitational waves but also calculates their trajectory and adjusts its position in an instant. It's a monumental engineering challenge, but one that could redefine how we think about space travel. Despite these obstacles, the potential rewards are immense. Gravitational wave surfing could offer a fuel-efficient, high-speed method of travel, allowing us to explore distant star systems without the limitations of traditional propulsion. It's a concept that blends the beauty of physics with the boldness of human ingenuity, reminding us that the universe itself might hold the keys to our future exploration. As we continue to explore the possibilities of space-time curvature, let's turn our attention to another intriguing idea: advanced wave detection and utilization, and how future technologies might make gravitational wave surfing a reality. Now, let's take a closer look at how future advancements in technology could bring the dream of gravitational wave surfing closer to reality. The key to making this concept work lies in our ability to detect and utilize gravitational waves with unprecedented precision. While current detectors like LIGO have already proven that we can observe these ripples in space-time, the next step is to develop systems that can not only detect them but also interact with them in meaningful ways. One promising avenue is the development of ultra-sensitive detectors capable of picking up even the faintest gravitational waves. These detectors would need to be far more advanced than what we have today, potentially leveraging breakthroughs in quantum sensing and nanotechnology. Imagine a network of detectors spread across the solar system, working together to create a real-time map of gravitational wave activity. This network could provide the data needed to predict the arrival and trajectory of these waves, giving spacecraft the information required to position themselves for a successful surf. But detection is only half the battle. To truly harness gravitational waves for propulsion, we'd need technologies that can convert their energy into motion. This could involve creating materials or systems that resonate with the frequency of gravitational waves, effectively locking onto them and transferring their energy to the spacecraft. Think of it as tuning a radio to a specific frequency, but instead of sound, you're tuning into the vibrations of space-time itself. Such materials might rely on exotic properties like negative mass or advanced metamaterials, which could interact with gravitational waves in ways that traditional materials cannot. Another exciting possibility is the use of artificial intelligence and machine learning to optimize wave detection and navigation. AI systems could analyze vast amounts of data from gravitational wave detectors, predicting wave patterns and calculating the optimal trajectory for a spacecraft in real time. This would require immense computational power, but with the rapid advancements in quantum computing, such capabilities might not be as far off as they seem. Of course, these technologies are still in the realm of speculation, but they represent the kind of bold thinking needed to turn gravitational wave surfing from a theoretical concept into a practical reality. By combining cutting-edge science with innovative engineering, we could unlock a new era of space travel, one where the universe itself becomes our highway. As we continue to push the boundaries of what's possible, let's turn our attention to another fascinating idea: cosmic strings as highways, and how these hypothetical structures could revolutionize our understanding of space-time travel. Now let's shift our focus to a concept that sounds like it's straight out of science fiction but is rooted in theoretical physics: cosmic strings as highways. Imagine a universe crisscrossed with incredibly thin, incredibly dense threads of energy cosmic strings. These hypothetical one-dimensional defects in space-time are thought to have formed during the early moments of the universe, and if they exist, they could offer a revolutionary way to travel across vast distances in the blink of an eye. Cosmic strings are theorized to be under immense tension, creating a gravitational field so intense that it warps space-time around them. This warping effect could allow objects traveling along a cosmic string to effectively ride the curvature of space-time, bypassing the limitations of conventional propulsion. Think of it like a cosmic zipline where the string itself acts as a guide, pulling you along at incredible speeds without the need for fuel or engines. But what makes cosmic strings particularly intriguing is their potential to connect distant parts of the universe. If we could locate and map these strings, they might serve as natural highways linking star systems or even galaxies. This would drastically reduce the time and energy required for interstellar travel, opening up possibilities for exploration and colonization on a scale we can barely imagine. Of course, cosmic strings are still purely theoretical, and their existence has yet to be confirmed. However, their properties are grounded in well-established physics, such as general relativity and quantum field theory. If they do exist, detecting them would require incredibly sensitive instruments capable of observing the subtle distortions they create in space-time. Some scientists have even proposed that cosmic strings could leave behind detectable signatures, such as gravitational waves or unique patterns in the cosmic microwave background. The potential applications of cosmic strings are as vast as the universe itself. Beyond travel, they could provide insights into the fundamental nature of space-time, offering clues about the early universe and the forces that shaped it. They might even serve as cosmic laboratories, allowing us to test theories of quantum gravity and other phenomena that are currently beyond our reach. As we explore the possibilities of cosmic strings, it's clear that they represent a tantalizing glimpse into the future of space-time travel. While the challenges are immense, the rewards could be equally extraordinary. Next, we'll delve into the practicalities of navigating these cosmic highways and the technologies that might make it possible. Now, let's take a closer look at what it would actually take to navigate these cosmic strings. While the idea of using them as interstellar highways is thrilling, the reality is that finding and traveling along these hypothetical threads would be no small feat. One of the biggest challenges lies in detecting cosmic strings in the first place. These structures are thought to be incredibly thin, possibly no wider than a proton, and yet they stretch across unimaginable distances. To locate them, we'd need instruments capable of picking up the faintest distortions in space-time, far beyond what our current technology can achieve. Once detected, the next hurdle would be mapping their paths. Cosmic strings aren't static, they're dynamic, moving and vibrating through space. This means that any navigation system would need to account for their ever-changing positions and orientations. Advanced computational models and real-time tracking technologies would be essential to keep up with these shifts, ensuring that spacecraft could safely and accurately follow the string's trajectories. But even with precise mapping, traveling along a cosmic string would present its own set of challenges. The intense gravitational fields surrounding these strings could pose significant risks to any spacecraft venturing too close. Without proper shielding and propulsion systems, a ship could be torn apart by the immense forces at play. This means that future spacecraft would need to be equipped with materials and technologies capable of withstanding extreme conditions, as well as propulsion systems that can adjust to the unique dynamics of traveling along a cosmic string. Another consideration is the energy required to navigate these cosmic highways. While cosmic strings could theoretically reduce the energy needed for interstellar travel, harnessing their power would still demand advanced energy sources and efficient propulsion methods. Concepts like antimatter engines or zero-point energy extraction might come into play, but these technologies are still in their infancy and would require significant breakthroughs to become viable. Despite these challenges, the potential rewards of navigating cosmic strings are immense. Not only could they revolutionize space travel, but they could also provide us with unprecedented insights into the nature of the universe. By studying these structures, we might uncover clues about the early moments of the cosmos, the behavior of space-time, and even the elusive theory of quantum gravity. As we continue to explore the possibilities of cosmic strings, it's clear that the journey to harness them will be as complex as it is exciting. From detection to navigation, every step will require innovation, collaboration, and a deep understanding of the universe's most fundamental forces. Next, we'll turn our attention to another fascinating concept: space-time loops and how they could redefine our understanding of travel through time and space. Now, let's shift our focus to a concept that sounds like it's straight out of science fiction, but is grounded in real theoretical physics: space-time loops, also known as closed time-like curves. Imagine a path through space and time that loops back on itself, allowing an object or even a person to return to the same point in space and time where they started. This is the essence of a closed time-like curve, or CTC for short. While it might sound like a plot device from a time travel movie, CTCs are a serious topic of study in physics, with implications that could redefine how we think about travel and time itself. So, how do these loops work? In simple terms, a closed time-like curve occurs when the fabric of space-time is bent in such a way that it creates a loop. If you were to follow this loop, you could theoretically travel back to an earlier moment in time, effectively allowing for time travel. This idea is rooted in Einstein's theory of general relativity, which suggests that under certain extreme conditions, such as near a rotating black hole or in the presence of exotic matter, space-time could be twisted into these loops. But here's where things get tricky. The existence of CTCs raises some mind-bending paradoxes, the most famous of which is the grandfather paradox. Imagine traveling back in time and accidentally preventing your own birth. If you were never born, how could you have traveled back in time in the first place? This paradox highlights the logical inconsistencies that arise when time travel is introduced into the equation. Physicists have proposed several ways to resolve these paradoxes. One idea is the self-consistency principle, which suggests that any actions taken within a closed time-like curve must be consistent with the events that have already occurred. In other words, you couldn't change the past in a way that creates a contradiction. Another theory involves the concept of parallel universes, where traveling back in time would create a new timeline, leaving the original one unchanged. While these solutions are speculative, they offer intriguing possibilities for how CTCs might function without breaking the laws of physics. Beyond time travel, closed time-like curves could also revolutionize rapid transit. If we could create or harness these loops, they might allow us to traverse vast distances in space almost instantaneously. Picture this: a spacecraft enters a CTC, loops through space-time, and emerges at its destination in what feels like no time at all. This could make interstellar travel not only possible but practical, opening up the cosmos in ways we can barely imagine. Of course, the challenges are immense. Creating or finding a stable closed time-like curve would require technologies and energy sources far beyond our current capabilities. We'd need to manipulate space-time on a scale that's currently only theoretical, and we'd have to navigate the complex physics that govern these loops. But as we've seen throughout this exploration of space-time curvature, the universe is full of surprises, and what seems impossible today might just be the breakthrough of tomorrow. As we wrap up our discussion on space-time loops, it's clear that the possibilities they present are as fascinating as they are complex. From redefining our understanding of time to unlocking new methods of travel, CTCs challenge us to think beyond the limits of our current knowledge. Next, we'll dive into another groundbreaking idea: the concept of stabilizing these loops and what it would take to make them a reality. Now, let's take a closer look at what it would take to stabilize these mind-bending space-time loops. While the idea of closed time-like curves is fascinating, the reality is that creating and maintaining them is no small feat. One of the biggest hurdles is the need for exotic matter, a hypothetical substance with negative energy density. This exotic matter would be essential for keeping the loop stable, as it could counteract the natural tendency of space-time to collapse or unravel under extreme conditions. Without it, the loops would simply fall apart, making time travel or rapid transit impossible. But what exactly is exotic matter, and how could we even begin to produce it? Exotic matter isn't something we can find lying around in nature. It's a theoretical concept that arises from certain solutions to Einstein's equations, and it behaves in ways that defy our everyday understanding of physics. For example, it would have the ability to repel rather than attract, creating the kind of negative pressure needed to keep a closed time-like curve open. While we've yet to discover or create such matter, advancements in quantum physics and particle accelerators might one day bring us closer to this goal. Another challenge lies in the sheer scale of energy required to manipulate space-time in this way. We're talking about energy levels that dwarf anything humanity has ever produced. Some theories suggest that harnessing the power of entire stars or even black holes might be necessary to generate the conditions for stable CTCs. This raises questions about not just the feasibility of such technologies, but also the ethics and consequences of wielding that kind of power. Could we even control it, or would it spiral beyond our grasp? Beyond energy and exotic matter, there's the question of how to navigate these loops safely. Even if we could create a stable closed time-like curve, traveling through it would require precise control over the forces at play. One wrong move and the loop could collapse, trapping or destroying whatever entered it. This is where advanced physics comes into play. We'd need a deep understanding of the interplay between gravity, quantum mechanics, and the fabric of space-time itself to ensure safe passage. Despite these challenges, the potential rewards are staggering. Stabilizing closed time-like curves could revolutionize not just travel, but our entire understanding of the universe. Imagine being able to send information or even people across vast distances in an instant, or exploring the mysteries of time itself. While the road to achieving this is long and fraught with obstacles, the pursuit of such knowledge pushes the boundaries of what we believe is possible. As we move forward, the next step in our journey will explore how these theoretical concepts might intersect with practical technologies. What would it take to turn these ideas into reality, and what breakthroughs might be on the horizon? The answers could reshape our future in ways we can only begin to imagine. Now, shifting our focus to another groundbreaking concept, let's explore how dark energy could become the key to unlocking the secrets of space-time travel. Dark energy, the mysterious force driving the accelerated expansion of the universe, has long puzzled scientists. Unlike gravity, which pulls objects together, dark energy seems to push space itself apart. This unique property makes it a fascinating candidate for manipulating space-time in ways that could revolutionize how we travel across the cosmos. The theoretical basis for dark energy propulsion lies in its ability to influence the fabric of space-time on a cosmic scale. If we could somehow harness this force, it might allow us to create localized distortions in space-time, effectively bending it to our advantage. Imagine a spacecraft equipped with a dark energy propulsion system, capable of warping space-time around it to reduce travel distances or even achieve faster than light speeds. While this sounds like science fiction, the underlying physics suggests it's not entirely out of reach. Currently, our understanding of dark energy is still in its infancy. We know it makes up about 68% of the universe's total energy content, but its exact nature remains one of the biggest mysteries in modern physics. Some theories propose that dark energy is a property of space itself, often referred to as the cosmological constant. Others suggest it could be a dynamic field, similar to the Higgs field, but with vastly different effects. Regardless of its true nature, the potential to tap into this immense energy source is tantalizing. One of the biggest challenges lies in figuring out how to interact with dark energy. Unlike conventional energy sources, dark energy doesn't seem to interact with matter in the same way. It doesn't emit light, absorb radiation, or exert a direct force on objects. This makes it incredibly difficult to detect, let alone manipulate. However, advancements in astrophysics and quantum mechanics might one day provide the tools needed to bridge this gap. For instance, future technologies could allow us to create devices that generate or control dark energy fields, opening the door to entirely new forms of propulsion. As we continue to unravel the mysteries of dark energy, the possibilities for space-time travel grow ever more intriguing. Could this enigmatic force be the key to bending the universe to our will? While the road ahead is filled with unknowns, the pursuit of understanding dark energy could lead to breakthroughs that redefine our place in the cosmos. Next, we'll delve into the practical applications of dark energy and how it might be harnessed for propulsion, bringing us one step closer to turning these theories into reality. Now, let's take a closer look at how dark energy could be practically applied to revolutionize space travel. While the concept of harnessing dark energy remains speculative, scientists and engineers have proposed several intriguing ideas that could one day make this a reality. One such idea involves creating a dark energy propulsion system that manipulates space-time itself. By generating a controlled dark energy field around a spacecraft, it might be possible to create a localized warp bubble, effectively compressing space in front of the craft and expanding it behind. This would allow the spacecraft to ride the distortion, potentially achieving speeds that surpass the limits of conventional propulsion. Another speculative technology involves the use of dark energy reactors. These hypothetical devices would tap into the energy of the universe's expansion, converting it into a usable form of power. While the specifics of how this could work are still unclear, some theories suggest that advanced quantum technologies might allow us to interact with dark energy on a microscopic scale. For instance, quantum vacuum fluctuations, tiny ripples in space-time, could be harnessed to generate energy. If we could amplify and control these fluctuations, it might provide a steady source of power for dark energy propulsion systems. One of the most exciting possibilities is the idea of dark energy sails. Similar to solar sails that use the pressure of sunlight for propulsion, dark energy sails would utilize the repulsive force of dark energy to push a spacecraft forward. This concept relies on the ability to create materials or fields that can interact with dark energy, effectively catching its expansive force. While this remains purely theoretical, advancements in materials science and quantum field theory could one day make it feasible. Of course, the challenges are immense. Dark energy doesn't interact with matter in the same way as other forces, making it incredibly difficult to detect, let alone manipulate. However, breakthroughs in astrophysics, quantum mechanics, and energy generation could pave the way for practical applications. For example, the development of ultra-sensitive detectors capable of measuring dark energy's subtle effects might provide the first step toward harnessing it. Additionally, advancements in artificial intelligence and computational modeling could help us simulate and test dark energy interactions in ways that were previously impossible. As we continue to explore these possibilities, the potential for dark energy to transform space travel becomes increasingly compelling. While the road ahead is filled with unknowns, the pursuit of understanding and harnessing this mysterious force could lead to breakthroughs that redefine our capabilities in the cosmos. Next, we'll turn our attention to another fascinating concept: the holographic universe and how it might offer a completely new approach to space-time travel. Now, shifting our focus to a concept that feels like it's straight out of science fiction, let's explore the holographic universe and its potential to revolutionize space-time travel. The holographic principle is a fascinating idea that suggests our three-dimensional reality might actually be a projection of information stored on a two-dimensional surface, much like a hologram. Imagine the entire universe as a cosmic movie screen, with everything we see and experience being a kind of projection from this underlying framework. If this principle holds true, it could open up entirely new ways of thinking about travel across the cosmos. At its core, the holographic principle proposes that all the information about a volume of space can be encoded on its boundary. This means that, in theory, the universe could be thought of as a vast hologram, with every star, planet, and galaxy being a kind of image projected from this boundary. For space-time travel, this raises an intriguing possibility. If we could manipulate the information on this boundary, we might be able to project matter or even entire spacecraft across vast distances instantaneously. Instead of physically moving through space, we could simply reprogram the hologram to place us at our desired destination. One of the most exciting implications of this idea is the potential for faster-than-light travel without violating the laws of physics. Since the holographic principle suggests that space and time are emergent properties of information, it might be possible to bypass the limitations imposed by the speed of light. By altering the underlying information, we could effectively teleport from one point in the universe to another, making interstellar travel as simple as updating a cosmic database. However, the challenges are immense. First, we would need to develop a deep understanding of how the holographic principle operates on a practical level. This would require breakthroughs in quantum physics, information theory, and computational power. Second, we would need to find a way to interact with and manipulate the information on the universe's boundary, a task that currently lies far beyond our technological capabilities. But as our understanding of quantum mechanics and the nature of reality continues to grow, the possibility of harnessing the holographic universe for travel becomes increasingly tantalizing. As we ponder this mind-bending concept, it's worth considering how it could transform not just space travel, but our entire understanding of reality. The holographic principle challenges us to think beyond the limits of our three-dimensional experience and imagine a universe where information is the fundamental building block of everything. Next, we'll dive into another groundbreaking idea: the role of quantum foam in creating microscopic space-time tunnels and how they might be scaled up for travel. Now, let's take a closer look at what it would take to turn the holographic principle from a mind-bending theory into a practical tool for space-time travel. Engineering holographic travel would require overcoming some of the most complex challenges in science and technology. At the heart of this endeavor is the need to manipulate the very fabric of the universe's information, a task that demands unprecedented advancements in computational power and quantum technologies. First, consider the sheer scale of the computational challenge. If the universe is indeed a hologram, every bit of information about its contents, every star, planet, and particle, would need to be encoded and processed. To manipulate this information, we would need computers capable of handling data on a scale that dwarfs anything we have today. Current supercomputers, while powerful, are nowhere near capable of simulating even a fraction of the universe's complexity. We're talking about systems that would need to operate at the limits of what's theoretically possible, potentially harnessing the power of quantum computing to perform calculations that are currently unimaginable. Quantum technologies would play a crucial role in this effort. Quantum computers, with their ability to process vast amounts of information simultaneously, could provide the computational muscle needed to interact with the holographic boundary. But even with such advanced tools, the challenge of decoding and manipulating the universe's information would be immense. We would need to develop entirely new algorithms and programming languages designed specifically for this purpose, as well as methods to interface with the holographic framework itself. Another major hurdle is the physical manipulation of the holographic boundary. if we're to reprogram the universe's information to enable travel, we would need a way to interact with this boundary directly. This could involve creating devices capable of detecting and altering the underlying information, perhaps using advanced quantum sensors or even entirely new forms of technology we haven't yet imagined. The energy requirements for such devices would likely be astronomical, pushing the limits of our ability to generate and control power on a cosmic scale. Beyond the technical challenges, there are also profound philosophical and ethical questions to consider. If we gain the ability to manipulate the holographic universe, what does that mean for our understanding of reality? Could we inadvertently alter the fabric of existence in ways we can't predict? These are questions that would need to be addressed as we move closer to making holographic travel a reality. Despite these challenges, the potential rewards are staggering. The ability to project matter across the cosmos instantaneously would revolutionize not just space travel, but our entire relationship with the universe. It's a vision that pushes the boundaries of what we think is possible, inviting us to imagine a future where the stars are no longer out of reach. As we continue to explore the mysteries of the holographic universe, we're reminded that the journey to the stars is as much about understanding the nature of reality as it is about building the tools to traverse it. Next, we'll explore another fascinating concept, the role of quantum foam in creating microscopic space-time tunnels and how they might be scaled up for travel. Now, shifting our focus to another intriguing possibility, let's explore the concept of quantum foam and its potential to create microscopic space-time tunnels. Quantum foam is a term used to describe the turbulent, frothy nature of space-time at the smallest scales, where the fabric of reality is thought to fluctuate wildly due to quantum mechanics. Imagine space-time not as a smooth, continuous surface, but as a bubbling, ever-changing sea of tiny, interconnected tunnels. These fluctuations, though incredibly small, could hold the key to unlocking new ways of traversing the cosmos. At the quantum level, space-time is anything but static. Particles and energy pop in and out of existence, creating a chaotic, dynamic environment. Within this quantum foam, microscopic tunnels could form, connecting distant points in space-time. These tunnels, often referred to as quantum wormholes, are theorized to exist for fleeting moments before collapsing back into the foam. The challenge lies in finding a way to stabilize and enlarge these tunnels, transforming them from fleeting phenomena into usable pathways for travel. Scaling up these microscopic tunnels would require overcoming significant hurdles. First, we'd need a way to detect and isolate these quantum wormholes, which are far too small and short-lived to observe with current technology. Advanced quantum sensors capable of operating at the Planck scale, the smallest measurable unit in physics, might be necessary to even begin this process. Once detected, the next step would be to stabilize them, preventing their immediate collapse. This could involve manipulating the energy and matter within the tunnels, potentially using exotic forms of matter or energy to keep them open. The energy requirements for such an endeavor would be immense. Stabilizing and enlarging a quantum wormhole would likely demand energy levels comparable to those found in the cores of stars or even black holes. Harnessing this energy would require breakthroughs in energy generation and control, possibly involving technologies like zero-point energy extraction or advanced fusion reactors. Even then, the process of scaling up these tunnels would need to be precise, as any instability could render them unusable or even dangerous. Beyond the technical challenges, there are also theoretical questions to consider. For instance, how would these tunnels interact with the surrounding space-time? Could they create unintended distortions or ripples that affect nearby objects or even the fabric of the universe itself? These are questions that would need to be addressed as we move closer to making quantum foam tunnels a viable option for travel. Despite these challenges, the potential of quantum foam tunnels is immense. If we could harness and scale them up, they could provide a way to traverse vast distances in the blink of an eye. bypassing the limitations of conventional space travel. It's a concept that pushes the boundaries of our understanding of space-time, inviting us to rethink what's possible in the realm of interstellar exploration. As we continue to probe the mysteries of quantum foam, we're reminded that the universe is far stranger and more wondrous than we often imagine. Next, we'll delve into the idea of multiverse travel and how space-time curvature could create bridges between parallel universes. Now, let's take a closer look at what it would take to stabilize and enlarge these quantum foam tunnels, turning them from fleeting quantum phenomena into practical pathways for travel. One of the biggest hurdles is the inherent instability of these microscopic tunnels. At the quantum level, space-time is in a constant state of flux, with particles and energy appearing and disappearing in a chaotic dance. To stabilize these tunnels, we'd need to find a way to counteract this natural tendency to collapse, essentially freezing them in place long enough to be useful. One potential solution lies in the use of exotic matter or negative energy. These theoretical substances could provide the necessary counterforce to keep the tunnels open. Exotic matter, for instance, has properties that defy our everyday understanding of physics, such as negative mass or energy. By introducing this material into a quantum foam tunnel, we might be able to counteract the forces that cause it to collapse. However, the existence of exotic matter is still purely theoretical, and producing or harnessing it would require breakthroughs in both physics and engineering. Another challenge is the energy required to stabilize and enlarge these tunnels. The energy demands would be astronomical, potentially rivaling the output of entire stars. To meet these demands, we'd need to develop new ways of generating and controlling energy on an unprecedented scale. Technologies like zero-point energy extraction, which taps into the energy inherent in the vacuum of space, or advanced fusion reactors, capable of producing vast amounts of energy with minimal waste, could play a crucial role. But even with these technologies, the process of scaling up a quantum foam tunnel would need to be incredibly precise, as any imbalance could cause the tunnel to collapse or become unstable. Advanced material science could also be key to stabilizing these tunnels. Imagine creating a kind of quantum scaffolding made from materials that can withstand the extreme conditions within a quantum foam tunnel. These materials would need to be incredibly strong, yet flexible enough to adapt to the dynamic nature of space-time at the quantum level. Developing such materials would require a deep understanding of quantum mechanics and nanotechnology, as well as the ability to manipulate matter at the smallest scales. Beyond the technical challenges, there are also theoretical questions to consider. For example, how would stabilizing a quantum foam tunnel affect the surrounding space-time? Could it create ripples or distortions that impact nearby objects or even the fabric of the universe itself? These are questions that scientists would need to explore as we move closer to making quantum foam tunnels a reality. Despite these challenges, the potential rewards are immense. If we could stabilize and enlarge these tunnels, they could revolutionize space travel, allowing us to traverse vast distances in an instant. It's a concept that pushes the boundaries of our understanding of space-time and invites us to imagine a future where the stars are within reach. As we continue to explore the mysteries of quantum foam, we're reminded that the universe is full of possibilities waiting to be unlocked. Next, we'll dive into the fascinating idea of multiverse travel and how space-time curvature could create bridges between parallel universes. Now, let's shift our focus to an even more mind-bending concept, the idea of using space-time curvature to create bridges between parallel universes. This theory, often referred to as multiverse travel, suggests that the fabric of space-time could be manipulated to connect our universe with others, opening up entirely new realms of exploration. The theoretical basis for this idea comes from the concept of the multiverse, which proposes that our universe is just one of many, each with its own unique physical laws and properties. One way to imagine these bridges is through the lens of space-time curvature. Just as a wormhole could connect two distant points within our universe, a space-time bridge could potentially link two separate universes. The key lies in understanding how space-time behaves under extreme conditions, such as near black holes or during the early moments of the Big Bang. In these scenarios, the curvature of space-time becomes so intense that it might create pathways or bridges to other universes. The potential applications of multiverse travel are as vast as they are speculative. For one, it could allow us to explore entirely new forms of matter, energy, and even life that exist under different physical laws. Imagine discovering a universe where gravity is 10 times stronger or where time flows backward. The scientific insights gained from such exploration could revolutionize our understanding of physics and the nature of reality itself. However, the challenges are equally staggering. Creating and stabilizing a space-time bridge would require an unprecedented level of control over gravitational forces and energy. We'd need to find a way to generate the immense energy required to bend space-time to such an extreme degree, and then maintain that curvature without causing catastrophic disruptions to our own universe. Additionally, navigating these bridges would require advanced mapping and safety protocols, as the laws of physics in another universe might be completely alien to us. Despite these hurdles, the concept of multiverse travel invites us to dream big. It challenges us to think beyond the confines of our own universe and consider the infinite possibilities that lie beyond. As we continue to explore the mysteries of space-time curvature, the idea of connecting with parallel universes remains one of the most exciting and ambitious frontiers in science. Next, we'll delve into the challenges of navigating these multiverse bridges and what it would take to make such journeys a reality. Now, let's take a closer look at what it would actually take to navigate these multiverse bridges. Imagine stepping into a spacecraft designed to traverse the boundaries between universes. The first hurdle, mapping the unknown. Unlike traveling within our own universe, where we have star charts and gravitational landmarks, multiverse travel would require entirely new methods of navigation. We'd need advanced systems capable of detecting and interpreting the unique signatures of other universes, which might operate under completely different physical laws. Think of it like trying to read a map written in a language you've never seen before, except the language is the very fabric of reality itself. Safety would be another critical concern. Crossing into another universe isn't as simple as stepping through a doorway. The transition could expose travelers to extreme gravitational forces, radiation, or even unknown forms of energy. To mitigate these risks, we'd need robust shielding technologies and fail-safes to protect both the crew and the spacecraft. And let's not forget the possibility of encountering entirely new forms of matter or energy that could behave unpredictably. Imagine encountering a substance that defies our understanding of physics. How would we even begin to prepare for that? Then there's the challenge of communication. If we were to establish a bridge to another universe, how would we stay in contact with our own? The laws governing communication, such as the speed of light, might not apply in the same way. We'd need to develop entirely new methods of transmitting information across these cosmic divides, potentially relying on quantum entanglement or other speculative technologies. But perhaps the most daunting challenge of all is the sheer unpredictability of what lies beyond. Even with the most advanced mapping and safety protocols, there's no guarantee that we'd fully understand the environment of another universe until we're already there. This raises profound questions about risk management and ethical considerations. Should we even attempt such journeys if the consequences are so uncertain? Despite these challenges, the pursuit of multiverse travel pushes the boundaries of human ingenuity. It forces us to think creatively, to develop technologies and strategies that might seem impossible today. And while the road ahead is fraught with obstacles, the potential rewards discovering new worlds, unlocking the secrets of alternate realities, and expanding the horizons of human knowledge are nothing short of extraordinary. As we continue to explore the possibilities of space-time curvature, the dream of navigating multiverse bridges remains one of the most thrilling and ambitious frontiers in science. Next, we'll explore how dark energy could play a role in manipulating space-time for travel, opening up even more possibilities for the future. As we wrap up our journey through these 25 groundbreaking theories, it's clear that the manipulation of space-time curvature holds the key to unlocking a future of interstellar and even inter-universe travel. From wormholes and Alcubierre drives to black hole slingshots and multiverse bridges, each concept pushes the boundaries of what we once thought possible. These ideas aren't just science fiction, they're rooted in the cutting-edge science of today, offering a glimpse into a future where humanity could traverse the cosmos in ways that defy our current understanding of physics. What's truly remarkable is how these theories challenge us to think beyond the limits of our technology and imagination. They remind us that the universe is far more complex and interconnected than we often realize, and that the answers to some of our biggest questions might lie in the very fabric of space and time itself. Whether it's harnessing dark energy, stabilizing quantum foam tunnels, or navigating cosmic strings, each theory represents a step toward a future where the stars are no longer out of reach. But the journey doesn't end here. The exploration of space-time curvature is just beginning, and the possibilities are as vast as the universe itself. Imagine a world where travel between galaxies is as routine as a cross-country flight, or where we can step into alternate realities and witness the birth of new worlds. These aren't just dreams, they're the potential outcomes of the ideas we've explored today. So, what do you think? Could one of these theories become the foundation for the next great leap in human exploration? The future of space-time travel is waiting to be written, and it's up to us to stay curious, ask questions, and keep pushing the boundaries of what's possible. If you're as excited about these ideas as we are, don't forget to hit that like button, subscribe for more deep dives into the future of science and technology, and ring the notification bell so you never miss an update. The universe is full of mysteries, and together we can uncover them. Until next time, keep imagining, keep exploring, and keep reaching for the stars.